Hi everyone, in this video I am reviewing all of the equations on the equation sheet. Okay, so the mean, sum of squares, and variance equations are all ones that you should be very, very familiar with. So that's this group of equations right here. Your mean is always the total of all of your scores divided by the number of scores. Okay, so M is for mean. Your scores are represented by X, and N is always the number of the thing that you have summed all of. So in this case, the number of all the scores. Okay, now to get the sum of squares, you take the deviation scores, square them, and sum them all up. So this uppercase sigma character, this uppercase sigma, always means add up all the things. Okay, sigma for sum, uppercase sigma for sum. Okay, so you always want to work from the inside out. So you start by taking these deviation scores. Okay, so a deviation score is how much does a given score, remember X is score, how much does a given score deviate from that mean that you calculated? So what's the difference between the score and the mean? Okay, so you have a deviation score, and then you square it. So you do that for each of your scores, and then you sum them all up. So sum of squares, SS, is the sum of squared deviations. So deviation, square it, sum it. Okay, once you have the sum of squares, this can go into two different equations. Okay, now you can just see that you match this SS to those SS's. These two equations are equations for variance. The difference between the two equations is whether you are dividing by n or dividing by n minus 1. Notice here that this lowercase sigma is a Greek letter. Compare it to this lowercase s, which is a Latin letter. When you have Greek, that is always going to be your population parameters. When you have Latin, those are your sample statistics. So which equation you choose depends on whether you're working with the entire population or just a sample. Okay. Now, if you get variance, which is what we have circled here, to get standard deviation, you always take the square root of that. So standard deviation is either lowercase sigma or s. So to get from sigma squared to sigma, you take the square root. To get from s squared to s, you take the square root. Okay. Now, in many cases, rather than working with a distribution of scores, we're working with a distribution of means. So that's what this subscript m means. The subscript m means distribution of means. Now, to convert the variance of a distribution of scores to the variance of a distribution of means, you divide by n, right? You divide by your number of scores. Now, if you have the standard deviation of the distribution of means, again, you're just going to take the square root. So sigma sub m is the standard deviation of the distribution of means. If you have a population, to get from this one to this one, you just take the square root. Same if you're working with the standard deviation of distribution of sample means. Again, you divide by n to go from the distribution of scores to the distribution of means, you divide by n, and then to get from variance to standard deviation, you take the square root. Okay. Clean this up. Okay, so now that we've reviewed those 6 equations, let's move on. Okay. These right here are test statistics. So these are the stats you calculate when you're doing a hypothesis test. Notice that for z, you have sigma in the denominator. Remember, sigma comes from over here, and that's when you're dealing with a population. So if you know sigma, you're going to use a z-score. In the t-score, you have s sub m in the denominator. So s over here, remember, is if you have a sample. So if you don't know the population parameter, you use the sample as an estimate, and that means you have to use a t-score. Okay. In the numerators here, you have 2 different options for your z-score. Your regular z-score, you are comparing a given score to the population mean. So again, we have Greek meaning population, so that is a Greek lowercase mu, which is a Greek m. So in this equation here, you have just your regular sigma. Now this next z equation, this one here, we are comparing a mean to the mean of the distribution of means. Okay, so in this first one, we're working with scores. In this second one, we're working with means. When you get down to the equation for t, we are also working with means. So you have your sample mean, and again, the mean of the distribution of means. Now, this is often a hypothesized mean that is given in the problem. Okay. Moving on to confidence intervals. Okay, confidence intervals. So, here you have the mean. Notice that it's an m, not a mu, so this is a mean calculated from your sample, plus or minus the test statistic, right? So note that these are not calculated from this. These are from your lookup table, right? So these are your critical scores. So based on your degrees of freedom and your level of significance, you use the table to look up what the critical score is, what the cutoff would be, and that's what goes in that spot. Right, so we have sigma sub m. So you take this, bring it over here, and you square root to go from the variance to the standard deviation. Same thing here. Right, here you have variance, and you're going to standard deviation. And lastly, we have our equations for effect size. In the top version, you are using sigma because you know the population standard deviation. In the bottom one, you're using S because you have to estimate it using the sample standard deviation. For both cases in the numerator, you have your sample mean minus the population mean. So really, it's very similar to calculating a z-score, right? Because here you're comparing the mean to the sample mean, or sorry, the sample mean to the population mean, and you're dividing by standard deviation, so you're turning it into units of standard deviation. So what D tells you is how many standard deviations your sample mean is from that population mean, much in the same way that Z tells you how far your score is from your mean. Okay, moving on to the equations for the independent samples t-test or independent groups t-test. That's this line right here. That's that whole line. Okay. Before we do that, let's go back to this one really quick. This t equation works for both a single sample and a dependent samples t-test or paired samples t-test. The only difference between a single sample t-test and a paired sample t-test is that for the paired one, you're using different scores. So in that case, you take the after score minus the before score because you want the sign of that difference to match the direction of change, right? So if something increases, you want that difference to be positive. So you take the difference between the after score and the before score, and then you use those different scores just like you would your regular scores, right? So you add them all up, divide by the number of scores to get the mean, so the average difference score, and then you do the sum of squares and the variance and the standard deviation just like you would for a single sample t-test. Okay, so moving on to your two samples, dependent or independent samples t-test. So here, all you have to do is work from left to right across the page. In this first equation, you're going to see df, which is degrees of freedom. Remember that df is just n minus 1. So df sub x is the degrees of freedom for the first group, df sub y is the degrees of freedom for the second group, and df total is dfx plus dfy. Now, to get this variance, so s squared sub x is variance of sample x. We just use this regular variance equation that we've been using the whole time. And you use the same equation to calculate variance for the second sample, sample y. Okay. So once you have S2 pooled, you see that it goes in the numerator of this next step. So you take S2 pooled and you divide by n. Now you do this for each sample. If your samples are the same size, you're going to have the same variance of the distribution of means for both samples. If your samples are different sizes, this number is going to be different because n is going to be different. So once you have S2m, you match it in the next equation. That goes over here and over here, right? This first one is for sample x. The second one is for sample y. That's why you did it twice. And that gives you the variance of the distribution of the difference of means. So that's just s squared sub difference. And we match that over here. But notice that in the t equation, just like we had before, that denominator is just the standard deviation. It is not the variance. So to get from here to here, we take the square root. Okay. Now the confidence interval is very similar to the one we saw before. So here's a confidence interval. Here's a confidence interval. Now, as with the previous one, T is not calculated. This T is your critical T-score from your lookup table. Okay? In this one over here, we're using a mean because we're just looking at a single list of values. Here we use the two sample means because we're comparing those two sample means. In this one, we used S sub m, which is the same as the denominator for your t-score. Over in this one, we're using S sub difference, which is the same as the denominator in your t-score. Okay. Now for effect size, D, again, we are taking differences, right? We're taking differences and dividing by S pooled. Okay. Excuse me. So if you look at our previous equation for D, we had m minus mu divided by just the regular standard deviation, right? Not the standard deviation of the distribution of means. So over in this one, since we have two sets of scores, again we're taking the difference, and taking the difference, and then like over here we use the regular standard deviation. S pooled takes the place of the regular standard deviation. So it's really the same process for all of the different types of t-scores, except that you have a couple adjustments in the middle for the independent samples. Right, you do a little bit extra for the independent samples t-test. Now let's move on to the equation for the one-way between groups ANOVA. So the one-way between groups ANOVA is an extension of the independent samples t-test. If you did that worksheet that I posted before the second midterm, you'll recall that the p-value you get if you do this process with two samples and this process with the same two samples, you'll get the same p-value, right? So a one-way ANOVA, a one-way between groups ANOVA, is just like an independent samples t-test, except you can do it with more than two groups. Okay. When I revised the equation sheet, I added in these brackets because I noticed that many of you were having issues with order of operations. So now that you have brackets, hopefully this will help you remember that you do all of the inside stuff before you sum, right? So you take the deviation, square it, and multiply by n before you add everything up. Okay, now again, you don't really have to memorize any new equations. All of these equations use things you should already know. Okay. So to calculate the mean, use the same equation as before. So what you're doing here is just like you took deviation scores before to calculate the sum of squares, except you're taking the deviation between the mean and the grand mean instead of scores and the mean. Right? So to get the regular mean, you add up all the scores and divide by the number of scores. To get the grand mean, you add up all the means and divide by the number of means, right? So it's the mean of means. Now, this direct approach only works if all of your samples are the same size. If they aren't, then you have to take a weighted average of the means. Okay. So, deviation, square it, multiply by the sample size, so the size of that individual sample for each mean that you're looking at. Right? Each sample has its own mean and its own n. Right? So you do this for each of your samples and then you add them all up. And then you add them all up. Now the degrees of freedom is the number of groups minus 1. And your textbook uses the abbreviation MS for mean squared, but really this is the same thing as variance, right? S squared sub whatever. Up here, you've got your sum of squares divided by your degrees of freedom. Down here, you've got your sum of squares divided by your degrees of freedom. So you take this first value, divide, equals. Okay, same thing over here. You have your first sum of squares, divide by degrees of freedom, equals. And once you have these two MS values, you just turn that into a fraction. Right, that's your numerator, that's your denominator, equals, and that gives you your test statistic, F. Same in the total row. Right? So there were no equations that you needed to memorize here. You just need to recognize the symbols that you've been using all along. And then R squared, we're just pulling things from the table that you already have, right? You have SS between and SS total. So R squared gives you the proportion of sample variance that is accounted for. You don't need to know what that means, but just know that all you have to do is use the information that you've already calculated. Okay, now on to the equations for the one-way within groups ANOVA. If you look at this row, you will see that it is exactly the same as this one. Now, the way that you know that you have a within groups ANOVA is that you have a row for subjects, right? That's because you're using the same subjects, you're using the same participants repeatedly if it's a within groups design. Okay. And then the row for within changes somewhat, but again, you're just using things that you already have in this table, right? So if you have sum of squares total minus sum of squares between minus this one. Okay. Now, what's different in this table is that you have two different F ratios. In both cases, the denominator is within. Right? It's the mean squares within. Same like it was up here. What's different is that you are taking this one to go into that numerator, and this one to go into that numerator. Okay. Now again, you don't have to memorize this. It's all labeled for you, right? If you're in the MS column and the subjects row, this is MS subjects. So over here you see MS subjects. You just match it up and move on. Okay. Okay, now we've got your two-way ANOVA, and it works the same as the previous two tables. It's just that these tables get bigger and bigger the more variables you add. Okay, so here you've got means, grand means. You just have some subscripts for rows versus columns. Now, if you look at the last page of the syllabus, you'll see that I don't expect you to calculate all this stuff from raw scores. Rather, if I give you a partial table right, a table with some of this information filled in, you should be able to fill in the rest of the table. So if I gave you all of this information, right, all of the sums of squares and degrees of freedom information, for example, you should be able to calculate the mean squares and the F ratios. And these mean squares and F ratios work exactly the same as they did in those previous two tables. Right? You've got between rows, so you find the sum of squares between rows and divide by df between rows. Right? So you have sum of squares divide by df gives you ms. Sum of squares divide by df gives you ms. Sum of squares divide by df gives you ms. Right? This happens across the table for the whole table for every single ANOVA possible. Okay. Now for the F ratios, again, you're just matching things up. So again, the denominator is always within, right? So as with the other two tables, you're taking ms within and putting that in the denominator. And just like we did before, the thing next to it is what goes in the numerator. Easy peasy. Okay. Now moving on to something different. Here we have equations for correlation and regression. Now, for correlation, you have a new symbol. This is our first new symbol since the very beginning of this document. We've got R. So R is the Pearson correlation coefficient. Now, the word correlation describes a relationship between two continuous variables. What we were looking at before is you had a continuous dependent variable, but a categorical independent variable, right? So up in these equations, you are comparing groups. The thing that divides the participants into groups is a categorical independent variable. For example, a treatment group and a control group. With correlation, you do not have groups. Rather, you have two scores for each participant, their score on variable x and their score on variable y. And you're looking for a relationship between those two scores. Okay. So, to calculate the Pearson correlation coefficient, you first find the mean for variable x and the mean for variable y. You then take the difference between each score and the mean, right? So the deviation scores, just like we did before, for each x and each y, and these x's and y's are paired. Remember, each participant has one x and one y. So you take those deviation scores and you multiply them, and then you're going to take those products of the deviation scores, the thing you get when you multiply, and then you're going to add all of those up. And that gives you your numerator. In the denominator, you have the product, the sum of, in the denominator, you have the square root of the product of these sums of squares. So you calculate sum of squares for variable x, you calculate the sum of squares for variable y, multiply those two values and take the square root, and that gives you R. Okay. Now, to get from the correlation coefficient to the regression equation, we have to use some method of calculating the slope and the intercept. I prefer using these ones down in this box because it's a lot easier. You already have all of the information that you need. Okay, so if you calculated R using this equation, you have that. It's the exact same thing right here. So you already calculated that, plug it in the equation for B. Over here, you already had to calculate sum of squares sub x, so you plug that in the equation for B. You now have B. So you take B, you plug it in to this equation for A. You already have the two means calculated, so you put those in here and you solve for A. Then you put these values into your regression equation. So y hat is the predicted value of y. A is the y-intercept, which we calculated right here. B is the slope, which we calculated right there. And then x just stays as is. So that way, if you are given a value of x, you can plug it into that equation. You've already got A and B, and you solve for y. You solve for y hat. Right? Y hat is the predicted value of y. So given some x, you can solve for what you expect y to be. Okay, now on to our last group of equations. The final test statistic that you learn in this class is chi-squared. So chi looks like an uppercase X. Now, what separates chi-squared from all of the other equations you've learned so far is that it's a non-parametric test. That means that you aren't working with ratio or interval scale variables. This works with categorical variables. So if your independent variable is categorical and your dependent variable is categorical, you're going to do a chi-squared. Okay? Now, to calculate chi-squared, regardless of whether it's a goodness of fit or an independence test, you always use the same equation. To do this, you have your observed frequency, that's the count of the number of times something falls into a certain category, and you have your expected frequency. Now that expected frequency comes from over here, and it is based on some expected distribution. If you're doing a chi-square for independence, you expect the same proportions across different categories. If you're doing a chi-square for goodness of fit, you're given some specific distribution. For example, you expect 60% in category A, 30% in category B, and 10% in category C. Right? So to do that, you take your total number of observations, multiply by those different percentages, and that gives you how much you expect in each of those categories. Okay. And then for each category in your table, you do observed minus expected, then you square it, and then you divide by expected. And you do that for each cell in your table, and then you add them all up, and that is your chi-squared score. Okay. Now, looking at the degrees of freedom equation, if you have a table that has just one row of things, K is your number of groups, and you subtract 1. So if you have 3 categories, your degrees of freedom is going to be 2. Okay. If you have a two-way table, so you have multiple rows and multiple columns, you take your number of rows minus 1 and your number of columns minus 1. Okay, so if you have a table that's got 1, 2, A, B, C, right? Your number of rows is 2 minus 1, be 1. Your number of columns is 3 minus 1 is 2. So 1 times 2 equals 2, and that's your degrees of freedom. Okay, and I think that is the end of my review of the equations. If you have any questions, please post a reply to this video.